Okay, good morning. All right, today we're going to finish up 14.7, continuing with the second derivative test that we saw last time. Okay, so remember from last time that if we solve fx equal to 0 and fy equal to 0, we get a bunch of critical points. And then to tell what they are, we need to use the discriminant, that d function, where d is defined as f double x, f double y, minus fxy squared, right? And you remember that if d of ab is positive, and f double x of ab is positive, we have a what? Both positive, we get max, min, saddle point, minimum, right? If d is positive and f double x is negative, then we have a local maximum. And if d is negative, and then regardless of what f double x is doing, we have a saddle point. Finally, you won't see this case in this class, but just be aware that if you ever get d equal to 0, this is when the test is inconclusive. And you're going to need a different way to figure out maximum and minimum. But we're not going to cover that particular case. Whatever other ways you need to do, they're far more complicated than what we're going to be doing here. So we're only going to encounter the first 3 cases in this class. Okay, so I'll leave that there because we'll be using that. Whoa, fuzzy. There we go. We'll be using that for this next example. In this example, we want to find a point on a plane (3x plus 2y plus z is equal to 6. That is closest to the origin. All right, so we got this. Of course, the plane contains an infinite number of points. Suppose it looks like that. Think of it as the floor in this room right here. That's the plane we're talking about. And the origin could be my hand right here. So what's the point closest to my hand? Well, obviously, you can see it's the point directly below my hand, right? That's basically what we need to be doing here. This is our origin, and some point on this plane, call that x, y, z. And if you calculate the distance, call that d, that point will give you the smallest distance among all the other points on the plane. In other words, we want to minimize the distance. to the point 0, 0, 0. That's the origin. And intuitively, we know that's the point that's going to be perpendicular to the plane. Right? If you draw a line, that line will be perpendicular to the plane. Okay? So, we need to work with distance. Let's get the distance formula out. Some random point on the plane will have a coordinate that's x, y, z. We want to go to the origin. So x minus 0 plus y minus 0 plus z minus 0 squared, and the whole thing under a radical. And that will give us the distance from any point on this plane to the origin. If the point is not origin, then obviously these zeros will be something else. But we're dealing with the origin, so they all turn out to be 0. At this point, notice that this thing we're working with here has 3 variables. We can work with 3 variables with the test we learned last time. That d function is a 2-variable function, and everything we saw last time rests upon the assumption that we're dealing with a 2-variable function. So a 3-variable function is not going to be workable for us. We got to reduce down to 2. So what do you think we can do? What is something we can do to reduce this equation from 3 variables to 2 variables? Think about how x, y, z are related. Yeah. These 3 x, y, z can't be any random x, y, z. They have to be sitting on that plane, right? So if x, y, z have to be constrained on the plane at all times, that means those 3 will have to satisfy this equation. All right, so let's take the plane equation, 3x plus 2y plus z is equal to 6. Solve for one of them, whichever one you want. Here I'm going to solve for z. Z doesn't have a coefficient more than 1, so it'll be the simplest thing to solve for here. And this tells me that I can choose x and y basically however I wish, but whatever x and y I choose, z has to obey this equation. The last variable here, the last coordinate, is a dependent variable upon the 2 independent variables. So I'm going to substitute this into here. And here we got the equation that we need to work with. We'll find the critical points, find that d function, and test the critical points. The first thing before you do any differentiation, notice that we got this square root here, we got square. It's going to end up being quite messy. So we're going to take advantage of the fact that distance is a positive quantity. So that means minimizing d is equivalent to minimizing d squared, right? Because if d is positive, d squared will also be positive. So whatever can make d as small as you can, a positive quantity, it's also going to make d squared as small as it can. So instead of working with d with the square root, we're going to work with d squared. Get rid of that square root, and things will be a little bit easier than that, than dealing with d. And let's just call this d squared function, let's call that f. Right? This new function, f, we're calling f, is really square of the distance. Now we can use the second derivative test. Now we're down to a problem that we have dealt with last time. Right? A function of two variables, find the critical points, find d, etc., etc. All right, so let's do that. Let's see. fx, we get 2x out here. We're going to get negative 6 times 6 minus 3x minus 2y. And all of these guys will be 0. Let's simplify this a little bit. Let's see, we get 20x plus 12y equal to 36. Everything is reducible by 4 actually, reducible by 4. So 5x plus 3y is equal to 9. Okay, so that's one equation we're going to have to work with. We'll call it equation 1, and we'll come back to it after we get fy, just like last time. All right, next equation, fy, same idea, right? 2y minus 4 times 6 minus 3x minus 2y. We like this to be 0. So just keep doing the same thing, a little bit of algebra. 2y minus 24 plus 12x plus 8y equal to 0. 12x plus 10y is equal to 24. Reducible by 2. So that's equation 2. Okay, so as usual, you get your system of two equations of two unknowns. You have to find x and y that will satisfy both equation 1 and equation 2. And it's typically not hard. It's just potentially a little messy. Okay, let's do the simplest thing we can do. Let's find equation 1 in terms of one variable sub into the second one. From equation 1, for example, we can solve for, I don't know, y. We see y is equal to 3 minus 5 over 3. X. Substitute that into 2, and then we can solve our equation. You know how to do this stuff. Right, we're just doing algebra now. This is very, very Simple stuff. After a few quick algebra steps, you should get x is equal to 9 over 7. If you know x, you know y from this equation up here. And y turns out to be 6 over 7. Okay? Okay, next step. In principle, we have to find that d function and then check whether this will be a maximum or a minimum. But before we do that, maybe we don't even have to do that. Let's use what we know from our physical intuition. If you're talking about a point on the plane to the origin, some other point right here, there is no such thing as a maximum distance because this plane extends forever. Whatever point you can find that has a distance, I can find another point with a bigger distance. So there's no such thing as a maximum distance from a point to a plane. Does that make sense? So that means that whatever critical point we found has to be a minimum, right? From our physical intuition, this has to be a minimum. So we can actually skip all of that d test. There's no maximum distance from a plane to a point. But there is a minimum. Which is the point that's directly below, using my hand and the floor as an example, the point directly below my hand would be the point that's closest to my hand. And we know that's the only critical point we found. So therefore, this got to be it. The only critical point must be the minimum. So therefore, we can skip that d test altogether. Forget about taking second derivative, forming fx, double x, double y, and all that stuff, and simply come to the correct conclusion without doing all that. All right, so the point x, y, z on the plane on 3x plus 2y plus z equal to 6 that's closest to the origin is 9 over 7, 6 over 7, and the last point we have to find is the z point on that plane. But if you have the equation of the plane, you can find z. Or you just have to look back just a little bit. To that equation, the same equation we used earlier to get rid of z in the distance. However you do it, you should end up getting 3 over 7. Yep, 3 over 7 for z. This will be exactly the same conclusion you would get if you actually went through with a d test, finding this f double x, f double y, fxy, and check all that stuff. You get exactly the same conclusion. But if you know what you're dealing with, you can take advantage and often skip that altogether. Does that make sense? Yes? Good. Any question on this one before we move on? Yeah. Well, a saddle point is neither a maximum nor a minimum. So again, we're dealing with the plane and the point. From just by looking at the situation here, we don't have a saddle point, right? We either have the minimum distance, which is right below my finger here, or we have a distance that's very, very big, and I just need to follow the plane forever. Does that make sense? So there's no point in this situation where it is not a maximum nor a minimum. But you're right. If we're not dealing with a plane, maybe a more complicated shape, then we can't be sure if we don't have a saddle point. In that case, the safe thing to do is to go ahead and check using the d-test. Good point. All right, so now we're going to talk about absolute maximum and minimum. So far, we've been dealing with local maximum and minimum. And now we're going to talk about absolute maximum and minimum. Local minimum means it's only relative to what's near that, but it's not globally the maximum or minimum. And once again, we're going to take advantage of the knowledge you have from one variable calculus. So you remember this, the absolute maximum and minimum of a function f of xy on the interval x is from a to b can occur at any interior critical point or on the boundary. Right? Remember this? Yes? Let me sketch a picture here, maybe you'll remember. Suppose this is A and this is B. So we only care about what's going on between A and B. And you got some kind of curve that looks like something like that, for example. We have three interior critical points. And we have two boundary points, right? And so here you can see the highest one is our absolute maximum, which occurs right here. And this guy here, this is our absolute minimum. It's the highest point or the lowest point on that graph within this interval that we care about. Whatever's going on outside, we don't care. But within this interval, we know what's going on here. Do you remember how to do this with a one variable function? Shall we do a quick example? Because we're going to need that concept for, let's do a very quick example to jot your memory, because we'll, like I said, we'll use that concept for a two variable case. Okay, let's see how much you remember. We're trying to find the absolute maximum and minimum of x squared minus 2x plus 3 on the interval minus 1 to 2. All right, so what do we do? Critical numbers first, okay? 2x minus 2 equal to 0, so that means x is equal to 1. And then what? And then what? All we gotta do is compare how high and how low they are, right? We just compare the functions, exactly. So we compare the function at the critical point, at the left end, at the right end. Whichever one is the highest one is my maximum. Whichever one is the lowest one is my minimum. So f at 1 is equal to 1 minus 2, that's 2. Minus 1 is 1 plus 3, plus 2 is 3, 6. 2, this is the 3. Okay, so here's my absolute maximum. And there's my absolute minimum, and that's nothing. That's just some other point. All right, do you remember doing this? Yes? We're going to be doing something very, very similar to this now when we transition to a two-variable function. Now, when we deal with two-variable case, we're looking for the absolute maximum and minimum of a two-variable function. Z is f of x, y. Which, remember, it's a surface, not a curve anymore. This is some kind of surface now. And over an interval, that's now defined by a region. For example, I got some kind of surface here. Notice the boundary now, the boundary, which I'm going to color with blue here. My blue pen is dead, so and I keep switching them, and I keep getting dead ones from the pile. Whatever. Okay. So you see the boundary now, this is a region. In the one variable case, it's just 2 points. Now we're talking about a region here. And that region, if you project it down onto the x and y plane, it might look something like that. But the basic idea is the same. Absolute maximum and minimum can occur anywhere at any of the interior critical points or anywhere on the boundary. any interior critical point or anywhere along the boundary. Okay? So it could be somewhere in the middle. It could be somewhere at the bottom end here. It could be somewhere here, here, here. We don't know. But just like in the one variable case, it's anywhere in the interior point and anywhere at the end of the interval that we care about. So the idea is the same, but the execution is obviously more complicated. Does that picture make sense? Does that idea make sense? Yeah? Okay, let's carry this out. Let's try this on some function that's not too difficult. Let's find the absolute maximum and minimum of f of xy is equal to 4x plus 6y minus x squared minus y squared plus 9. And now, to describe the boundary here, let me write down the notation. I'll explain what it means. On the set D, by the way, this D has nothing to do with the second derivative test D, just some name. All the points x, y such that x is between 0 and 4 and y is between 0 and 5. Okay, so what this means is that all the points x comma y, that straight line in this context means such that, and these two things are, you know what they mean. Okay, so that's what it means. We got this surface that's infinitely big, but we're going to just consider a portion of that. Consider the boundary that's set up by this situation here. Let me show you what the picture looks like. All right, so this is the surface we're talking about. It's a paraboloid of some sort. But we'll only consider a kind of a rectangular patch of that. The boundary, here's x. X is between 0 and 4. Y is between 0 and 5. So we have a little patch, and we're just looking at this little membrane here, looking for the absolute maximum and the minimum. And now you can see by inspection, we are probably going to find an absolute maximum somewhere in the middle of that patch. But notice that absolute minimum is going to be, just by inspection, somewhere probably at one of these corners. You got to remember that the maximum and minimum can occur anywhere on this patch and anywhere along the 4 edges. We have to check all of them. So I'll put a picture here, and we'll carry out the steps that we have to do. Okay, let's look at the region D. On the xy plane. We're talking about x is from 0 to 4. Let's say 4 is over here. Y is from 0 to 5. Let's say 5 is over here. So here we go. We have 4 edges here. And above this here, we have some kind of height determined by the equation. So that patch we just saw is going to be floating above this piece of paper. Right? Can you visualize that? Yep, that's what we're dealing with. It's got some height. We're looking for the highest point and the lowest point possible. And you got to remember that we need to find, first of all, the interior critical points. Then the maximum and minimum on each edge. And then we compare all of them, just like the one variable case. Okay, let's get the critical points first that we know how to do. We can get that very, very easily for x. I'm just rewriting the function here before I operate on it. Critical points, fx, 4 minus 2x is equal to 0. So this means x is equal to 2. Fy is equal to 6 minus 2y. We want this to be 0, so we see that y is equal to 3. And the interior critical point in this case is 2, 3. That's the only one. Only one that's not on the edge. That's why we call it an interior critical point. And because we saw the picture earlier, we know this is going to be a maximum, but we're going to verify that. Now we're going to check the boundaries. I'm going to label these 4 lines on the boundary as L1 down here, L2, L3, and L4. And we have to examine each of these. Let's look at L1 here. Notice that on L1, y is forever 0, right? Y is 0. So the 2 variable function we started with becomes a function of 1 variable because y is now 0. And it's going to reduce to purely f of x is equal to 4x minus x squared plus 9. And x is between 0 and 4, right? Okay? And this problem is identical to the simple problem we did earlier. Right? Exactly the same thing. Same kind of function, same boundary. We do that again on this boundary, then on L2, L3, L4. You see the big picture here? We're doing this problem 4 times on the boundaries, and then we worry about the interior points. All right, now we find the absolute and maximum minimum of this. So the critical point is 4 minus 2x equal to 0. This is x is equal to 2. So on L2, this function has a critical point, 2. And the ends are x is equal to 0 and x is equal to 4. Now we have 3 points to check on this boundary. The first one is at x is 0, y is 0. That's the corner. And then 2, 0. And then 4, 0. We're making a collection of points to compare later. The interior point we got very easily. And now on L1, we found 3 potential locations where this function can have a maximum or minimum, exactly like the one variable case. We're not going to worry about which one it is yet. I want to collect all the points first, and then compare all of them. Any questions so far? Doing okay? You get the idea here? Yes? All right, let's move to L2. When we go to L2, notice now x is a constant 4, and y can range from 0 to 5. So the 2-variable function we started with now reduces to a function of just one variable, y. And I'm skipping a little bit of algebra steps here, but you saw what we did with L1. All right, our 2-variable function reduces to 6y minus y squared plus 9, because x is 4 and y is now allowed to vary. And now we do the 1-variable problem one more time on L2. We find a critical point, 6 minus 2y equal to 0. This means y is equal to 3. And the ends are y equal to 0, y is equal to 4. Now we collect the points that eventually we have to consider. X is 4, y is 3. That's the first point. And then x is 4, y is 0. And then x is 4, y is 4. Sorry, where? Oh, 5, I'm sorry. Yes, it is. Yep. So what do I need to fix? This one, right? And notice that one of these points is duplicating what we found earlier. That's okay, right? That's okay. Because L1 and L2 share a point. So that point is the point we have to consider. That's fine. Now we move to L3. On L3, y is a constant 5, and x is allowed to range from 0 to 4. So the 2-variable function with y at a constant 5, x allowed to vary, reduces to 4x minus x squared plus 14. So we're back to a 1-variable calculus problem one more time, right? We find a critical number, 4 minus 2x equal to 0. This is x is equal to 2. and the ends are x is equal to 0, x is equal to 4. Our collection of potential locations are 2, 5, and then 0, 5, 4, 5. That's duplicating what we already have. Fine, no problem there. All right, now last edge, L4, the left edge of that boundary of the region D. Let's see. This time x is always 0. Y is allowed to vary between 0 and 5. So f of xy becomes f of just a function of y, and it's 6y minus y squared plus 9. Y is between 0 and 5. Do one variable calculus again. Y is equal to 3 is our critical point on that edge. Then the ends are y equal to 0 and y is equal to 5. And then 3 more points to consider. Some of those will be something we already have, and that's fine. 0, 3, 0, 0, 0, 5. All right? Okay, now all of these points could potentially be where a maximum or minimum is. So now we evaluate the two variable function fxy at all of these locations. Looks like we have 13 points, but many of those are duplicating. So we just have to plug all of those into fxy one at a time. All right, so we compare f of xy equal to 4x plus 6y minus x squared minus y squared plus 9 at those candidate points we found earlier. Okay, let me make a list of all just the unique ones. We're not going to duplicate them. 2, 3, that was our interior critical point. And then L1, we got these 3 points. And then L2, we had 4, 3. 4, 0, we already have. So we're going to go directly to 4, 5. And then on L3, we got 2, 5, 0, 5. And then 4, 5, we already have that. Finally, on L4, we had 0, 3, 0, 0, we got already, and then 0, 5, which we already have. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 points. All right, so this is pretty busy, but you see the idea? If you get the idea, then all of this is just a little bit of annoying work, but you see the big picture here, right? Yeah? Okay, now I put this into here. I'll do that for you. 22, 13, 9, 9, 18, 14, 18, 14, 18. And just like before, you pick out the biggest one here. That's our absolute max. Smallest one right here, there are two of them, absolute minimum. Very quickly, let's check out that picture we saw earlier. Okay, 2, 3 is the maximum, which we saw, right? Somewhere in the middle. And then minimum are 0, 0, 0, 4, right here and right here. That's exactly what we should be finding. Okay? All right, that's it. See you next time.